how to download and upload things from Agda, just now. So it's very secret. There's this little tiny icon right down here in the bottom right. That's it. That's the secret. So you click on this. So for one thing, any text that you paste in here will get put in here, and if you highlight any text in here, it shows up in here, and then you can select this and copy it and paste it somewhere else. Or there's a button here download files, right? So if you click on this, then here's all your files, and you can click on one to download it. So I don't know. Yeah, unfortunately, to upload a file, if you wanted to write a file on your computer and then upload it here, I think you just have to paste it into this box, and then it'll show up. It's a little bit indirect, but it is possible. So, well, and I guess there's another button here that says Activate Auto Synchronization with Clipboard. Not in Firefox. Okay, so I'm using Firefox, but maybe if you're using a different browser, maybe if you click that, it's anything that's in here will automatically be. You can just hit paste in another window, and it'll automatically. I'm not sure you can play with it, but. Yeah, and I think actually I realized, I'm not sure how this works. I think because I linked directly to this workspace, I think if you go here, you can actually edit it yourself, which is maybe a little strange if we come in here next time and someone has doing something. But whatever. I mean, yeah, you can obviously copy it and share it. All right. So my goal for today is to start to show you how we can use Agda to prove things about our programs. Okay, so this is something that, and this is one of the reasons that, this is certainly one of the places where functional programming caught on in industry early. There's places where people needed a level of assurance that their code didn't have bugs. That was a cut above the usual. Yeah, strangely enough, it's okay, there's different levels. There's I want my code to be generally correct, but there's going to be some bugs and other things, right? That's think about Microsoft Word. Microsoft certainly doesn't want Word to be super buggy because they want you to like it. But there's going to be bugs, and it's if it crashes, okay, maybe you lose a document. That sucks, but it's not like anyone's going to die if Word crashes, right? Or someone's going to lose $1 million. But there's another level of this software is trading my money on, high frequency markets. And if there's a bug, I could literally lose millions of dollars. I really want to be sure that it's correct. That's the kind of thing that people started using functional programming for. There's another level that's this program is flying a plane, and if there's a bug, people die, right? Strangely enough, that level doesn't use functional programming at all, because that level is so critical that there's tons and tons of rules about how you have to construct software and get it certified, and and it's standards that are were made 20 or 30 years ago, and so it's actually the kind of languages you are allowed to use for those kinds of super critical applications are pretty old-fashioned actually, because the standards it's so critical that they're not trying to keep up with the latest thing. They're just trying to make sure that everything is well tested and understood. So there's sort of this middle ground where. Also cryptography kinds of things. If you really want to be sure that your program doesn't leak secrets or whatever. So the point is, right, this is kind of one of the reasons that functional programming is used in those areas, because there's actually we have nice ways to prove things about our programs. And that's for a few reasons. Number one, because it tends to be kind of more mathematical, right? It's more focused on what things are equal to other things. You don't have a lot of side effects and stuff. It's easier to prove things about programs like in Haskell. And also, because of the Curry-Howard isomorphism, we can even use tools like Agda and there's other similar kinds of things where we can kind of combine the actions of programming and proving. We're not even we don't have to use a separate tool to prove stuff about our programs. We're kind of doing it on the fly. So that's our goal for today. I guess we kind of did that up here. We proved some stuff about is even, but very, very simple thing. I mean, what we're going to do today is kind of simple too, but we'll start down the path. So I want to prove, basically, here's our goal for today. You all know map, right? So we're going to prove that map. So if I have some list x's, and I first map a function g over that, and then I map f over that, okay, that turns out is the same as doing like map f compose g of x's. Hopefully this makes intuitive sense. I can either do kind of two passes where I first do f to everything and then I do g to everything, or I can do one pass where I just do the composition of I do like f and g to each thing. This is practical because this is like Haskell can kind of do this sort of optimization somewhat automatically. You can imagine if you see this pattern in your program, you can just automatically change it to this. It might be more efficient, or this is kind of a practical transformation we want to do. And maybe we believe it intuitively, but as a simple example, I want to see how we can formally prove this in Agda. Be like, yes, 100%. This is always true. Okay, so first we're going to have to define like lists and maps and stuff like that, which is all built in the standard library, but we're going to do it ourselves. So let's define lists first. So data list. And notice one interesting point, right? Before, like when we defined bool, right, we said, just bool is the set. Like bool is the type. So list by itself is not, so this wouldn't be correct. Because that's just saying list. Just list is a type. I can have something of type list. But we usually say it's a list of what? Like what is the type of the elements? Okay. So the way I can say that is I can say list is actually a function that takes a type and returns a type. Right? It's a function from types to types. So like list nat is a type, or list bool is a type, or whatever. And maybe you didn't think of it list as like a function before, because in Haskell, right, Haskell draws this strong distinction between I have functions that operate on values, and I have like polymorphic types that are separate things. In Agda, they're not really separate things. There's just functions, and functions could take types and return types, or they could take values and return values, or they could take values and return types, or whatever. Right? Okay, and what are the constructors of lists? We can actually use kind of this familiar notation. So I guess I actually have to say, how do I say this? I don't remember what okay, actually, you know what? Yeah, we can write it this way, for various reasons I don't want to really explain. We can also write it this way, and this is going to be better. This is really saying the same thing. It's parameterized by this type, but we're just going to be able to call it A and not, it's like the whole definition is parameterized by this type. So that type is not going to change. Every time I say list, I'm going to always say list A. Don't worry about it. I don't want to get into that. What's the difference between putting something on the left or right side of the colon? And honestly, even people that are like familiar with Agda sometimes get confused with this. But whatever. So empty set is list A, and I can make a cons, like an infix, which has type A, so list A, so list A. Okay, and this cons thing is you do backslash colon. So it's not two colons, it's a single Unicode character, which is a double colon. I mean, we could have write. No, probably we're not actually allowed to use this because colon means something special, right? Colon means something has a certain type. So this would probably be a syntax error. Let me just check. Oh, it's not. Huh. All good. And there is a way that, you know, you could tell Agda, hey, this list definition, please treat this as like a specially built-in list, and then you can use syntax like, you know, brackets A, comma, B, comma, C, stuff like that. We're not going to bother, so we'll just have to write our list to like 1 cons, 2 cons, 3 cons, empty list. But you can use other things. All right, let's define map. So what is the type of map? And what's the type of map in Haskell? And then we can think about how to translate it into that. Yeah.
A function of A to B, and then it takes a list of A and turns a list of B.
Right. And so, I love this. So this is an error, and it says not in scope A. So, and maybe we've seen this, but just want to emphasize, in Haskell, you can write a type like this. I mean, we would use lowercase letters. But even if I change it to lowercase letters, I'm going to get the same error. So in Haskell, if it sees lowercase things in a type, it's like, oh, those must be type variables. You must really want a for all. And so I'm going to like secretly add a for all for you to introduce those variables, right? So the for all is kind of what's defining those variables. Agda doesn't have anything like that. It doesn't like implicitly add that. We have to add that ourselves. You can actually use the notation for all in Agda, but just to keep things simple, right? Really, it's a function that takes first some arguments like A and B. It actually takes the types A and B and arguments first. Says, okay, what types do you want to use map with? Now you have to give me something of type A, B, and then what's the And, of course, often when we use map, we don't actually want to have to explicitly write down the types because it can figure them out. So we're going to actually put these in curly braces, which means we don't have to write this. So when we use map, it'll look exactly like when we use map in Haskell. And this really is, this really is what's happening in Haskell too. It's just that Haskell uses different syntax and doesn't require us to write this. It just kind of fills it in on that. So, all right. So now that should load okay. Let's make this bigger. There we go. Okay, we all know how to write maps, so let's pattern match on X's. If it's an empty list, we're going to return an empty list. If it's, I wonder what, if I say auto, it's probably going to do something weird. Yeah, that's not right. So then, yeah, just ignore the X. Just, not the X's, that seems, no, so just do X. Yeah, when you do auto, like, if it can find anything that has the right type, it'll fill it in. So it doesn't work as well when you're writing functions, because usually the type of a function kind of doesn't tell you enough about what you intend for it to do. When you're trying to prove a theorem, then typically we don't care what proof we have. As long as we have a proof, it's good enough for us. And so auto is great. If it can find something that has the right type, that means it's found a proof. We don't care which proof it is. But you know, you can use it. It's just hard to use it. Cool. Let's also define function composition. We're going to need that, right? Because we have this function composition here. So let's think about what is the type of function composition. This will be exciting. I will actually use so if I say \O, I think it gives me like the actual function composition symbol. I think you can also say like \circ, circle. All right. Well, let's start by saying, what's the type of function composition in Haskell, and then we can add some extra type arguments. Right? Does anyone know what the type of function composition is in Haskell? Any?
The function from A to B, function from B to C.
good. Unfortunately, this is actually backwards because, right, because we talked about this before, how like, we think of values flowing like left, when we write a type of a function, we write the input on the left and output on the right. When we write down a function application, we actually write the input on the right, and we kind of think of it, the output is coming out to the left, thanks to Euler. So, when we write F compose G, it's actually like X is input to G, and then like the output of that goes into F. So this actually needs to be like, you know, A to B is here, and then B to C is here. All right. Well, and then actually, this one is actually not that hard. I mean, really, all we have left is it doesn't know what A, B, and C are, and so we're just like, oh, those can just be arbitrary types. So we'll just add those as an implicit argument here, like that. Or 3 implicit arguments, right? But you can list multiple things of the same type all in one go. I could have also written like brackets A colon set, arrow bracket B colon set, arrow bracket C colon set. Okay, and then this is just define it like that. Cool. All right. Well, let's write down this theorem that we want, and then we can start trying to prove it. So, we'll call it map composition. So I really wanted to say like map F map to x's equal to map F equals x's, right? That's kind of my goal. But you know, it's like, well, what is F? What is G? What is x's? Right? So these are like, there's a whole bunch of arguments that I have to, right? I really want to say like for all F, for all G, for all x's, this is true. So those have to be extra arguments. So I have to say like, you know, F has some type, G has some type, x's has some type. Right. So what do you think? What should be the type of what should be the type of F and G?
Could F and G be just like the composition above?
Yeah, I think that's a good idea. Since we're going to use them in a composition here, it'd be nice if their types kind of match up with what we already named composition. Also, the point is like, this should work for any types, right? I don't care what types they are, as long as their types match up in the right way. So that it makes sense. So let's just say we'll assume B is C, G is A with B, X is, then what type is X's? List of what? A, right. Yeah, this is going to be input to G, map G. Okay, and if I try to load this, it's still going to be, it's like, what are A, B, and C? I don't know what those are. Okay, so we need yet more arguments that says, you know, A, B, and C are just whatever, arbitrary sets. Okay, so finally it accepts this as a type, and it just says, hey, you haven't defined it. Okay, so that's defined. So this is one of those things, like when I'm choosing which arguments to make like normal arguments and which arguments to make implicit, it probably feels like pulling a rabbit out of the hat and just like, oh, we should make these implicit. It kind of comes with experience. You figure out, really it has to do with when Agda is looking at the types of later things, will it be able to figure out the previous things kind of just by looking at those? So it can definitely figure out A, B, and C. For example, once it knows, the types of F and G, it's like, well, clearly I can see what types those are, and so I know what A, B, and C have to be. So you don't have to explicitly fill it in. It turns out in this case, we probably want to make F and G implicit as well. Actually, well, it cuts both ways. Let's leave them not for now, which will make it, I think, slightly easier to write the proof, and it would make it slightly more annoying to use, because you'd have to actually fill in F and G every time you want to use it. We could maybe try both. I don't know. And in general, you probably will, when you're doing Agda, you'll often run into like, oh, maybe I shouldn't have made this implicit. Maybe I should, or you kind of with the experience. All right, so let's try to prove this. We're going to run into some issues, and we'll maybe need some extra stuff. So we'll, rather than do it ahead of time, we'll just see what we need. Okay. All right. Well, how should I start? I have my F, I have my function G, and I have my list X's.
Pattern match on X's.
Yeah, pattern match on X's, right? Because the thing we're trying to prove says something about map, and like map, pattern matches on X's, and so we're going to need the pattern match on X's. So let's do that. Okay, let's see. In this case, we have to prove empty list equals empty list. Why is that? Well, if X's is the empty list, then it could look at this side and say, well, map of, I don't care what is, of empty list is empty list, just by definition of map. And then map of empty, it's just doing like, you get empty list. And the same on the right side. If X's is empty list, it really doesn't matter what functions we're mapping, it's just like reduces to empty list. So, that one is easy. The base case is often easy, right? It's just like, everything reduces to 0 or empty list or something, and you just do that. Okay, so now, this looks a little more interesting, right? So it has reduced it, right? It's says, okay, if the list is X cons X's, then I can like reduce map one step, right? Because map says, well, you get Fx cons a recursive call to map. So here we have like, it reduced both maps, right? So we got F applied to G applied to X, and then some recursive calls to map. And over here we have, of course, F compose G applied to X, and then the recursive call to map. So, why would these be equal? Well, we can say, okay, first of all, they're both conses, so that's good. And this part is equal to this part, and that's just by definition of composition. So actually, like we don't even need to do anything to convince Agda that this is equal to this, because they can just look at the definition of composition and see that that's what it is. Is this part equal to this part? And if so, why? Or how would we convince it?
My first thought would be that they're the same because the F and G of X in the first part and then the F composition of X are the same thing. So then the map parts have to be the same thing. If you remove the maps, they're the same. I guess.
Yeah, but I don't think that implies they're going to be the same. I mean, like, we're not just allowed to remove the maps, because, like, the maps might do something interesting that can somehow distinguish between them. So, I mean, this is what we're trying to prove, right? That they are the same. But so, anyone else? How would we prove that map F map G X's equals map F input G X?
Since we know that the first element is the
we're trying to prove, just like on slightly smaller lists. And so if we just make a recursive call, it's like, yeah, and then just, you know, through the rest of the lists. Hopefully this will come back. If not, we can always just do it on my computer instead of. Of course, I don't have all those things I just did, but do them quick. Let's see. So we have the list. And we had map. So okay. Hopefully, save everything. Oh, yeah, cool. Okay, yeah. So the idea is, oh, let me make this bigger again. Right. This part is equal to this part by definition. This part is equal to that part because we can make a recursive call to map comp. So here is a question for you. Like, so here we are. We're trying to prove something by writing a function, right? And one of the things that we often find ourselves doing is making a recursive call to the function, right? To like construct a proof. What would you call that in a math class? Anyone know? I would guess. That technique of like calling a proof recursively. It's called induction. That's what a proof by induction is. Right? It says, oh, suppose that law, which is really saying like, well, assume we can call this thing recursively on a smaller thing. Now we have to show it's also true for this bigger thing, right? So when we call the function recursively, we're using the induction hypothesis. And that's not just an analogy. Like, that's exactly precisely what's going on. All right, so the point is, the bigger point too, is that because we're proving something about lists and map, and lists are a recursive data type, map works recursively, right? We should expect that most interesting things we're proving about lists or map are gonna themselves, the proofs themselves are gonna be recursive. Because you're proving something about a recursive thing, so you kind of have to do some recursion to match the structure of the thing you're proving about. Okay? Or to put another way, you know, in more math terms, proving something about a recursively defined thing is probably going to be proved by induction. That's how we prove things about recursive things. All right. So, however, how do we actually do this? So we have a problem. The problem is, yes, we can make a recursive call to find out that map f map gx's equals map f compose gx's. But how do I turn that into a proof that like all of this equals all of this? Because that's not a proof of this. Like that's without this part. So kind of how do I add on this part? That's like, well, if these parts are equal, then I can add on these other equal parts in the beginning, and then the whole thing is equal. So we're going to need another property of equality, which is called And you maybe never thought about this as a property of equality before, because we just kind of take it for granted. Like, we take it for granted that anywhere, if I have a thing, let's say I know that x equals y, we kind of take for granted that anywhere I see x, even inside of a bigger expression, I could replace it with y. Right? But really what we're saying is, if x equals y, then this bigger expression with x in it is equal to the same bigger expression with y in it instead. Right? So that's called congruence. The fact that you can kind of like take an equality and use it as to build a bigger equality where it's just a piece. Okay? And so, how do we say this? We say, how do I explain this? The other question is, how do I express that idea of like having a thing that's part of a bigger thing? And the way we're going to express that is just by being like, if I have a thing, I can apply a function to it, and applying a function to it could like produce a bigger thing that it's part of, right? So I could have like x, but if I want to consider it as being part of the expression 3x plus 1, then I can say, well, consider the function that takes something called x and produces 3x plus 1 as output. Right? That expresses how the x kind of fits into that bigger thing. So congruence is going to say, look, you give me any function from A to B, and if you give me a proof that x equals y, then I will give you a proof that fx equals fy. We need some, let's see. So I need A and B are sets, and I need x and y have type A. Okay, so it says, for any type, doesn't matter what your types are, if you have any two things, x and y, that are of type A, and you also have a function from A to B that kind of says, it takes x and y and it kind of puts them in some bigger, potentially bigger context, right? If you give me a proof that x equals y, then I'll kind of show you that you can replace x with y inside of whatever thing it is. And this we're like, well, duh, because if you look at what this says, it's like, well, of course, like if you give a function two equal inputs, then of course it's going to give you equal outputs, right? You can't if I have two things that are like, oh, this function, of 3, as opposed to like the function applied to 1 plus 2. Like in math land, those have to give you the same output. It would be weird if f is like, oh no, you didn't give me 3, you gave me 1 plus 2, and that's different. So I'm going to output something different, right? Indeed, that can't happen in Agda. So, how do we prove this? Well, again, the proof is going to be very boring. Because, so I take my f, right? These are all implicit, so I don't have to write these, a, b, x, y. My first argument is f, and then here's a proof that x equals y. I have to produce a proof that fx equals fy. Well, if I just pattern match on this proof that x equals y, it can only possibly be REFL. Right? So the only way you can have that is if they're literally the same. And now, I just have to prove that fx equals fx, because now I know that x and y are the same. So again, proving this is not hard. It's just kind of inherent in the way that stuff works in Agda. But we can use this. We can now use this to prove some other things. So, how are we going to use this? Well, I want to say, and actually, you know what? Also, I'm going to do something else. I'm going to use something called Cong2. Let's see, how do we do this? We say, no, but let's think about what this means. This is basically, it's the same thing, except instead of a one argument function, we have a two argument function. So it's like, look, if you have the function f applied to x and z, and then the function f applied to y and w, if the first arguments are the same, or equal, and the second arguments are equal, then the whole thing is equal. Right? So if you can show me that, you know, these first parts are the same, x and y, and you can show me that the second parts are the same, then the whole thing is the same. The reason I think we're going to want this is because if you look here, right, we're saying, look, I've got cons applied to two things and cons applied to two things, and first I want to show that this is equal to this, and then I also want to show that this is equal to this, and I want that to tell me that the whole thing are equal. Okay? It just lets me like break it down into some smaller equalities. And again, I mean, the proof is just straightforward. All right, so I'm going to use that. I'm saying, look, I'm trying to prove that two things are equal, and those things are like some function applied to two arguments. In this case, the function is, you know, cons. It's cons applied to this, and over here it's cons applied to these other two things, and I want to show that the first parts are equal and the second parts are equal, and that lets me conclude that the whole thing is equal. So I'm going to say cons2, and the f that I want is cons. And I'm going to hit Control-C, Control-R for refine, which just says, all right, it needs some more arguments, so we're going to make those into wholes. Right? See, those arguments now, it's now broken it down for me into the two parts. Right? We have to show that f gx equals f compose gx, and we have to show that map f map gx is equals map f map f cons gx. So, this first one, it's just by definition of composition, right? So Agda actually can just like reduce the definition of composition and see that these are exactly the same. So in fact, if I just do like auto, if I say Control-C, Control-A, it should fill in REFL, yeah. Because they literally are the same once you reduce them both kind of according to definition. Okay. This one is, these are not equal according to definition, right? Because the definition of map we don't know what to do if we don't know whether x is you know, nebulous or con. So Agda can't reduce these any further, but we do know that they're equal because of, we can make a recursive called map comp, right? Or we could say because of our induction hypothesis. So I can just say map comp. And probably it could auto that, like if we do C, Control-A, yeah. You can fill in a recursive call. Questions? Let's do, I think we've got time for one more thing. So let's define fold R. Since the types A and B, and it's going to take, what function A, B, and a B, and it's going to take a list of okay, and we're going to define length. can, of course, define length. We could define it using full R. And so this is the next thing I thought of. Another simple example we can do to prove that, like, this version of length is equal to the one we can get with full R. So maybe I'll call it length. Length F, or length is full R, I guess. Oh, I just realized, by the way, this little subscript 2 do backslash underscore 2. So how do we define length with full R? So full R something something x's. By the way, this yellow color. So remember underscore. I guess I should. So I actually shouldn't put underscores there. I should put question mark. I was thinking about Haskell. But it's as good a time as any to mention, because sometimes there's an argument and you're like, you should be able to figure this out. I don't need to actually write this. The yellow color means like it's like I couldn't actually figure this out. So it type checked, but I don't really know what should go in this hole, so you need to fix that. But actually, I didn't really want underscores there because the point is, I know I need to fill these in. I just want to put. All right. And right, this is helpful. So this is the kind of thing I was encouraging you all to do. Like this is on, module 3 or whatever. To do this in your head, to think about, or on paper. Say, okay, if I'm folding this list, what's the type of fold R? And therefore, like, what are the types of the arguments to fold R? But of course, Agda can do this for, I guess Haskell can kind of do it for you too, but Agda's much better. So I was like, look, you've got two things to fill in. This one has to be a natural number, and this one has to be a function of type A to natural number to natural number. So the natural number that should go here is the length of the empty list, which is of course 0. And then the thing that needs to go here is the function that takes the first element of the list and the length of the rest of the list. It gives me the length of the whole thing. So this is just a function lambda. Oh, and actually, so let me show you something cool. Since I'm trying to fill in a function here, if I say Control C, Control R, so that's refine, right? That says, let's just like fill in this hole with something that's the right shape to have this type. So because it's a function type, they will fill it into lambda for us. If I say Control C, Control R, it says, okay, it's a lambda that's going to take 2 arguments, arrow, and you have to say what it outputs. Now, I don't care about x, so I can just replace this with underscore. And x1 is a terrible name. I'll call it, L for length, maybe. Reload. And then, of course, I want to do 1 plus L. I can also put L plus 1. But just looking at the way we define length, I know that it's going to be easier to prove that they're the same if I write the addition in the same order. Otherwise, we'll have to prove that addition is commutative, which we can do, but I'd rather avoid that for now. Okay, make sense? So now, we want to say, so length equals length F says for all types A, and for any x's, which is a list of A, it should be the case that length of x's equals length F of x's. Okay. Well, let's pattern match on x's, of course. Base case is probably going to be easy. 0 equals length F empty list. Well, what is length F empty list? Length F empty list is fold R something something empty list. And fold R on the empty list should reduce to that, the Z argument, which in this case is 0. So I suspect that Agda just hasn't reduced it all the way, and if it reduces it a little more, it'll see that these are actually the same. So I can just try, I can just try auto. You can always just try auto, right? You're like, if auto works, then great. Done. But so we just try it. Sure enough, even though those didn't look the same to us, it just hadn't reduced them fully. They were actually, all right. Now, here we have to prove that the successor of length x's equals length f applied to x con x's. And again, for whatever reason, it's decided that it thinks maybe we don't. I mean, to be fair to Agda, it is a difficult problem to know like how much to reduce things when it's showing you your goal. Because if it always reduced everything as far as possible, sometimes that could produce like completely ridiculously unreadable goals. Because it's like, oh, this function is actually defined to be this complicated thing, but I don't really care about that. I just care that it's like this function being applied to it. So it kind of tries to make some smart guesses about how much you want it to reduce, but it doesn't always, doesn't necessarily always correspond to exactly what we want. But we can look at this and we can say, wait a minute, so length f applied to x cons x's, that's fold r applied to x cons x's, and fold r applied to a cons is definitely going to be able to reduce by definition. Right? If we know that fold r is applied to a cons, we can reduce it to this. So it's going to be, you know, and this is where I wish, I don't know if you're using Agda, not in this website thing, but like on your computer, there are some commands you can type to be like, no, seriously, like please reduce it as much as you possibly can. Which would be helpful in this case because it would give us a better sense of what it is we're trying to prove. I don't know, I'll have to play with it. I think we're not going to be able to finish this today, so we'll have to play with it, and maybe we'll pick this up next time. But maybe there's a way to do it, or not really sure. All right, so we'll pick this up next time. We'll finish this.